Black holes. The very name conjures up images of vast, dark entities consuming everything in their path. The name alone makes you think of huge, dark things swallowing everything around them, pulling in stars, planets, and even light itself. These cosmic monsters are born when giant stars die in spectacular explosions known as supernovae. They're areas in space where gravity is so strong nothing, not even light, can escape. This boundary is called the event horizon. Imagine squashing our sun into something smaller than London. The result would be a black hole. That's how tightly packed they are, with immense density and gravitational pull. Black holes make us rethink how we understand space and time, warping the very fabric of the universe. They push the limits of what we know about physics, showing us how much we still have to learn about the cosmos. But inside these mysterious objects might be the answers to some of the universe's biggest secrets, waiting to be uncovered. One of the biggest puzzles is the information paradox, a mystery that has baffled scientists for years. This puzzle comes from a clash between two big ideas: general relativity, which explains how big things in space work, and quantum mechanics, which explains how tiny things work. Reconciling these could revolutionize our understanding. Figuring out this paradox could change how we see the universe and its basic rules, potentially leading to groundbreaking discoveries. It's a puzzle that's kept scientists busy for decades, and the answer might unlock even deeper secrets about reality, revealing the true nature of our universe. The information paradox comes from a basic rule in quantum mechanics: information can't be destroyed. This fundamental principle underpins much of what we understand about the universe at the smallest scales. This means we should be able to rewind the universe like a movie, tracing every tiny piece back to where it came from. Every particle, every wave should have a history that can be followed. But black holes seem to break this rule. They present a unique challenge to our understanding of physics. When something falls into a black hole, it seems to disappear, taking all its information with it. This disappearance is more than just a vanishing act. It defies the very laws of quantum mechanics. All that's left is the black hole's weight, spin, and charge, what scientists call the no-hair theorem. These properties alone can't account for the lost information. This is a problem because it means information is gone forever, which breaks the rules of quantum mechanics. The implications of this are profound and troubling. This contradiction is the heart of the information paradox. It represents a clash between two pillars of modern physics. It challenges what we know about both general relativity and quantum mechanics, suggesting at least one of these well-known theories might be wrong. This has led to intense debates and research in the scientific community. The information paradox isn't just a tricky problem for scientists, it's a puzzle that could redefine our understanding of the cosmos. It has big implications for how we understand the universe and our place in it. The resolution of this paradox could change our perception of reality itself. If information can really be lost, then the past and future become uncertain, and reality itself starts to seem a bit wobbly. This uncertainty could have far-reaching consequences for science and philosophy alike. In the 1970s, Stephen Hawking had a revolutionary idea that changed how we think about black holes. He said, black holes aren't completely black. Instead, they give off a faint heat glow, now called Hawking radiation. Hawking radiation comes from tiny energy bursts at the event horizon, the point of no return around a black hole. These bursts create pairs of tiny particles. One falls into the black hole and the other escapes into space. The escaping particle takes a little bit of the black hole's energy, making it slowly shrink over time. This discovery was huge because it meant black holes weren't the forever traps we thought they were. But it also made the information paradox worse. If black holes shrink away, what happens to the information they swallowed? Hawking thought the information was lost forever, but many other scientists disagreed. The search for an answer to the information paradox became even more important, leading to lots of new theories and ideas. One of the most interesting possible solutions to the information paradox comes from the strange world of quantum entanglement. This weird phenomenon, which Albert Einstein called spooky action at a distance, describes how two linked particles can affect each other instantly, no matter how far apart they are. Imagine flipping two coins at the same time, one landing on heads and the other on tails. This is similar to quantum entanglement, where what happens to one particle instantly affects its linked partner. Could entanglement be the key to understanding how information escapes a black hole? Some scientists think so. They suggest that information falling into a black hole gets linked to the outgoing Hawking radiation. This link would connect the black hole to the surrounding universe, letting information escape, though in a messy and hard-to-read form. Section 5. Non-violent, non-locality, rethinking information loss. The idea that information is saved through entanglement has led to a fascinating idea called non-violent non-locality. This theory, developed by researchers at Caltech and other places, suggests that information doesn't actually need to leave the black hole's event horizon to be saved. Instead, the information about the stuff falling in is stored in tiny connections within the Hawking radiation itself. These connections, coming from quantum entanglement, could keep the information safe even as the black hole disappears. Non-violent non-locality offers a convincing answer to the information paradox. It suggests that information isn't lost, just hidden in a complex web of quantum connections. But proving this theory is a huge challenge. To test these ideas, physicists are using a new tool, gravitational waves. Section 6. Gravitational waves, ripples in spacetime. Gravitational waves are ripples in space caused by the movement of heavy objects. Predicted by Einstein, these waves travel at the speed of light, carrying information about the things that made them. Imagine throwing a pebble into a pond. The ripples spreading out are like gravitational waves. Just as these ripples tell you about the pebble and the water, gravitational waves tell us about the objects that created them. Detecting gravitational waves in 2015 by LIGO started a new era in astronomy. It gave us a new way to study space, letting us see things that were invisible to telescopes. Gravitational waves give us a special chance to study black holes and maybe solve the information paradox. Section 7. Detecting the undetectable LIGO and the future of astronomy. LIGO, an amazing piece of engineering and teamwork, has two giant detectors in the United States. Each detector uses lasers and mirrors to measure tiny changes in space caused by passing gravitational waves. These changes are incredibly small, about 1,000th the width of a tiny atom part. But LIGO can detect them, letting us hear the universe in a new way. Detecting gravitational waves from merging black holes has already taught us a lot about these mysterious objects. But the future of gravitational wave astronomy is even brighter. New detectors like the planned Einstein telescope and Cosmic Explorer will be even better than LIGO, letting us detect fainter signals from further away. Section 8. Echoes from the abyss, gravitational waves and black hole information. Some physicists think gravitational waves might carry faint echoes of the information that falls into black holes. These echoes, hidden in the tiny ripples of space, could prove quantum entanglement and non-violent non-locality are real. Imagine shouting into a canyon and hearing faint echoes bouncing back. Similarly, gravitational waves might carry echoes of the information swallowed by black holes, giving us clues about what happens to it. Detecting these echoes is a huge challenge, needing very precise measurements and clever data analysis. But the reward is huge. If we can detect these echoes, it would be strong evidence that information isn't lost and would change how we understand black holes and reality itself. Section 9. Unraveling the Cosmos, the future of black hole research. Studying black holes and the information paradox is one of the most exciting and challenging areas in physics today. These enigmatic objects captivate the imagination of scientists and enthusiasts alike, pushing the boundaries of our understanding. It pushes what we know, making us confront the limits of our knowledge and come up with new theories to explain the universe. The quest to understand black holes forces us to rethink fundamental concepts in physics. The next few decades will be a golden age for black hole research. With rapid advancements in technology, we are on the brink of unprecedented discoveries. With new telescopes and detectors, we're ready to make amazing discoveries that could unlock the secrets of these mysterious objects. These tools will allow us to peer deeper into the cosmos than ever before. The information paradox shows how powerful human curiosity is and how we always want to learn more. It exemplifies our relentless pursuit of knowledge and our desire to solve the universe's greatest mysteries. It reminds us that the universe is full of mysteries waiting to be solved, and that the journey of discovery is just as important as the answer. Each step forward brings new questions and deeper understanding. By exploring the universe's most extreme places, we're not only learning more about space, but also understanding how everything is connected. This interconnectedness reveals the intricate tapestry of the cosmos. The information paradox, once a confusing puzzle, might hold the key to understanding reality itself. It challenges us to think beyond the known and venture into the unknown.